want to talk about how we start talking about classification, and in particular what the sort of framework we'd often talk about when we're talking about classifiers for sensory data. And this kind of starts to set the entire sort of flow in terms of different questions that one might want to eventually dig into, in terms of questions of classifiers, types of classifiers, how you might implement these. But to start, it's kind of important to get some things settled. So let's start there. The usual flow you might imagine is going to start from usually something of a sensor. Maybe it's a microphone. Maybe it's an imager. Maybe it's a set of sensors. Maybe it's something along the lines of something that tells you position. Maybe it's a chemical sensor. So be it. And what you want to be able to do is be able to go from the sensor result, which is typically an analog signal of some sort. You usually need to start with that and say, let me take this and first pull the signal out to something useful. Take that signal, enhance it. Maybe I'm going to do frequency decomposition. Maybe if it's an RF signal, I'm going to modulate it. A number of things. These are very important things. And then at some point, I've got something that looks more like signal. This is what we typically think of as a signal. When you finally got all these things, or a group of signals. And at this point, then we start talking about kind of feature detection. And there's many different things you might imagine here and words that you would hear. ANN being analog neural network, or other kinds of neural networks, or then you might have a deep neural network because it has many layers, or you might talk about all sorts of other things, and they're all kind of very similar. You might talk about things like Gaussian mixture models, which are a different kind of classifier that uses Gaussian structures. We'll talk about what is a winner-take-all in a moment, just briefly. But at this point, when you get to this, you have usually symbols or events, or something that is somewhat refined. We talk about information and data that's being refined at this stage. And that turns out to be important. This is typically now more discrete kind of symbolic representation. Often this might go into a processor, it might wake up a processor, it might do other things. We could still keep this in a continuous form if we wanted to. All right. So this is typically what we mean by an end-to-end computation. It'll go from a sensor all the way to a symbolic representation. It's analogous to thinking about other kind of just classical analog structures where you go, oh, let me take a microphone and I'll do some enhancement, and then maybe this detection is just simply a data converter. But then afterwards I'll do all of these things and maybe some other things in the digital processing. The way I've drawn this has not assumed anything, but it's also generalized everything. Okay? So the whole point is talking about from early sensor through signal to symbol refinement. And to look at this sort of signal to symbol part of it, we often talk about a number of different ways to do this classification. So we're often then going to talk about, well, there's going to be layers of that classification in a classical any sort of neural network kind of approach. Why layers? Well, we're typically meaning in that it's going to be a vector matrix multiplication plus some nonlinear functions. Okay, what do we mean? Nonlinear functions typically are these sort of tanh type of structures, right? Tanh is kind of a typical nonlinear function that's been used from early on. If you're familiar with analog circuits, you'll realize that the tanh is exactly what you use for a differential pair. It is also directly equivalent to the function you use for a Fermi-Dirac distribution function for those who are device physicists. And it is exactly that, and it comes from all of those physics and circuit concepts. It wasn't just came out of nowhere. And so we often talk about a layer as a vector matrix multiplication of a set of inputs and a nonlinear function. And what we find is that for a typical sigmoidal structure, which is tanh, which is what most people like to do, I need at least two layers, to be able to come up with this sort of computation such that I can do what is called a universal approximator, which in very simple language says, given I have a large number of inputs and outputs and middle node, which would be sort of how many hidden layer nodes, I can arbitrarily, to some extent, approximate any function. Now, eventually that number may need to be countably large, so countably infinite, but in theory I can do it. And to the precision I need the approximation, it works. And you think, oh, that's really cool. And this is the classical sort of two-layer neural network that people will talk about. And allows you to be able to do these things. Now, when I mean vector matrix multiplication, that's going to be in very simple case of having an output vector y as a function of an input vector x, and there's a weight matrix. Now, we're going to talk a lot about doing vector matrix multiplications in field programmable analog arrays for those who go into those discussions. There's a huge opportunity there. Sometimes we look at it there, sometimes we'll look at it in other places if we're getting into the analog space. Many different ways to do it, and we'll kind of keep it general at this point. But just know that for those who are familiar with these terms, you might understand that that's where that's going. And so when you look at these sort of structures, if I can build this in some form, in any technology I have to work with, that's what I would be trying to put together. What is interesting when I look at this is that, okay, well, how does this actually feel? Well, I might have some inputs where it's typically going to be a VMM, and when you draw this, it's typically, a VMM typically is a crossbar. And it's typically done as a mesh architecture, whether digitally or analog, if you're doing this in a parallel processing system. And even it's sort of the way we symbolically think about it, because all of this came and generated together. What you're going to realize is that you usually will talk about things going at 90-degree angles because of the crossbar. And then you'll go, oh look, now maybe I have a row of computation which are tangents, and then I could go into another vector matrix multiplication, and then another row of tangents. So there's sort of this 90-degree shift, and this is just part of how the architectures typically show up in a dense way, in mesh / crossbar, all these kinds of networks that you would build. Okay? So this works out well. The thing I do want to kind of connect with a little bit is to realize that another way to approach, there's other ways you can approach this. Now, the first, you go, well, do I need to use this as two layers? And the answer is, well, if I actually use what is a VMM plus what is a winner-take-all, which was mentioned up here, that changes the conversation. It no longer needs to be two layers. It can get away with one. That's a more complex question. But the problem that classically set this question is the XOR problem. It comes from the book Perceptrons, written in the late 60s by Marvin Minsky, which was basically, the key person who founded artificial intelligence. And you have to realize that artificial intelligence and machine learning / neural networks were not really on the same side for most of this sort of history. Okay. But history is a longer question. But very much those who did AI did not like the people who did neural networks, saw them as competitors, and wanted them to go away. And the book Perceptrons was entirely written for that reason. And the classical problem was to say, look, in a single layer, which would have been one VMM and one tanh function, I couldn't do an XOR problem. I couldn't do the XOR. In fact, it required two layers to do an XOR problem. I had to have a set of inputs, go into a first layer of these sigmoidal units, and then go into a second layer of these sigmoidal units. And so XOR is kind of the classic problem to talk about this. Now you could talk about the 3-input equivalent, which is 3 parity. You can talk about a 4 parity, and you can build on this. But all of these pieces give you a really clear understanding of, okay, why do I need to have multiple layered structures? Why is this so important? And also, what are the other trade-offs I'm going to run into if I actually want to start to work with the, other kinds of networks? What do I need to do in terms of building? And so forth.